Intermolecular forces are forces between molecules. We also refer to them as IMFs. And we can contrast intermolecular forces with bonding forces, which you are probably already familiar with, and those include ionic bonds, like sodium chloride. Those include covalent or molecular bonds, such as water. And they include metallic bonds, such as iron, which will be in a matrix. All right, and so these bonding forces, which we could call intramolecular, we often don't use that term, but they could be called intramolecular because they are stronger and they have shorter bonds. Now contrast that to the forces between molecules. So let's say you have liquid water and you have a bunch of water molecules, and there are weaker forces between them and between all of them. Or you can look at something like methane, and there's some weak force between them. Okay, so these are weaker than the bonding forces, and that's usually they're weaker. Occasionally they can be quite strong, and they're generally longer bonds, although we often don't refer to them as bonds. Okay, so look at that on a potential energy curve, and we've looked at where we have potential energy going up on this axis, and the x-axis is distance between nuclei. And we've looked at a curve, something like that, for covalent bonds. So that's a bonding force. And in contrast, so the distance, the average distance between the molecules would be given here, and the bond energy would be the difference between this part of the well and up here. So the bond energy would be this distance. All right, in contrast, intermolecular forces tend to be longer and weaker. So the average bond distance is longer, and the distance between the bottom of the well and separated nuclei is smaller. So they're longer bonds and they are weaker bonds. All right, let's look at 4 different types of intermolecular forces, and these are listed generally in order of strongest to weakest force. Okay, so the first is called ion dipole, and it's, for example, occurs when you have salts dissolved in water. Okay, but anytime you have an ion, like the cation of sodium chloride, for instance, and you have something with a dipole. Okay, water has a dipole. There will be an interaction between them with the positive side of the sodium and the negative side of the dipole in the molecule. Okay, another example, it doesn't have to be positive ions, it can be negative ions. You can have, oops, I didn't mean that, F minus. And that can also be bonded to water, but in this case it would bond to the more positive side of the water, the hydrogens. So those are both ion dipole forces. And some of these are very, very strong. All right, I'm going to skip hydrogen bonding for a minute and go down to dipole, dipole. And this is where you have 2 things with a dipole. Instead of above where you have an ion and a dipole, you have 2 dipoles, such as ICl. Okay, and you have a dipole, you have a more negative side and you have a more positive side of the molecule. And again, if you have another one nearby, there's also a negative side, or positive side here, and a negative side here. And the negative side of one molecule will be attracted to the positive side of the other, and that creates a weak bonding force. Okay, that's an intermolecular force, or a weak bond. This can also happen with anything with a dipole. So let's say we have pH3, and the phosphorus side would be attracted to the hydrogen side of the next molecule. Okay, so there's a weak a weak bonding force there. All right, so those are dipole-dipole forces. Anytime you have two things with dipoles, it will occur. All right, so back to hydrogen bonding, because it is a especially strong case of dipole-dipole interaction, and it occurs when you have a very electronegative atom, such as nitrogen, oxygen, or fluorine, bonded to a hydrogen. And what happens is that that very electronegative atom pulls electron density from the proton and therefore creates an especially strong attraction. Okay, hydrogen bonding occurs in water because water has an oxygen bonded to a hydrogen, so that oxygen, being very electronegative, pulls the electron density away from the hydrogens, so this hydrogen will be attracted to the oxygen of the next water over, and that is like a dipole-dipole interaction, but it's especially strong when you have nitrogen, oxygen, and fluorine, and so we call those hydrogen bonding, not dipole-dipole. Another example of that would be ammonia, which is going to look a lot like we did for pH 3 down here, except that it's much stronger. And it's much stronger because nitrogen is much more electronegative than phosphorus. So that's a similar type of interaction, but it's much stronger. It's hydrogen bonding. So anytime you have nitrogen, oxygen, or fluorine bonded to hydrogen, you can have hydrogen bonding. All right, then the fourth type is called dispersion. And that will occur even if there's no dipole whatsoever. If there's no polarity in the molecule, you can still have attraction. And why does that happen? Let's look at F2. Okay, even though there's no dipole there, the electron density is equally shared between the two of them. If there's another F2 nearby, like in a liquid state, you would still temporarily find the electron density can vary. Okay, so temporarily you might get a slight positive side on one and a slight negative side on the other, and when that happens temporarily, it will induce the next molecule over to follow suit, and the more positive side will be attracted to this negative side. So it'll induce the electron density to be pushed away from this side of the molecule and therefore create temporary dipoles in both. Okay, so it causes a temporary polarity in the other molecule. All right, and this can also happen with things like methane, which is completely nonpolar again. Okay, that's a nonpolar molecule, tetrahedral with all the groups being hydrogens. And yet there is attraction between them because temporarily one will have a slightly negative or positive side and will induce a temporary dipole in the other one. Okay, so dispersion, therefore, is present in all molecules. It tends to be, if these other forces are present, dipole-dipole, hydrogen bonding, or ion dipole, then it will be the weakest force, and therefore we usually talk about whatever's the strongest intermolecular force. But if there's no other intermolecular force present, you will always have dispersion. All right, and let's look a little more at dispersion and what creates greater dispersion or less dispersion. And remember, dispersion is caused by an induced dipole, okay, a temporary induced dipole. So we talk about the concept of polarizability, which is the ability to distort the electron orbital. So distort the orbital. And so the more polarizable, the greater the dispersion forces. So we can compare two things, two rare gases. We can look at neon bonded to neon and xenon bonded to xenon. And size makes a big difference. If you have a smaller molecule, it's going to be harder to create an uneven charge in it. Whereas if you have a larger molecule, you can create an uneven charge, and we can draw that in exaggerated form by showing the electron density swayed over to one side and that gets bonded to another one where the electron density is off-centered. So the electron crowd has been distorted, and you have a little bit more negativity on one side and a little more positivity on the other, and they're attracted. All right, so the conclusion is that the larger the size, the more polarizable. And if it's more polarizable, it's has greater dispersion forces. All right, we can compare another two things. We can look at hydrocarbons. CH4, methane, is a certain size, and if you have 3 carbons and hydrogens, it's going to be more polarizable because there's more electron density to move, to induce a dipole in. So this will be less polarizable, and this will be more polarizable. So we will have greater dispersion forces here. All right, so size makes a difference. The bigger it is, the more dispersion forces they will have. There's another thing that affects the size of the dispersion forces, and that is shape. If you look at these two molecules, you'll find that they have the same number of carbons and the same number of hydrogens. That actually makes them isomers, okay, where they have the same number of atoms, but they are different shapes. Okay, so we can compare these two, since they have the same size as far as mass, number of protons, neutrons, and electrons, we can compare their shapes. All right, and if you have an adjacent molecule to this one that is the same molecule, in other words, in a liquid form, they can line up. Okay, you can put another one right next to it, and you can have dispersion forces all along the chain. Okay, so that's a lot of dispersion. Whereas if you have more than one of these molecules in a container, they can't get that close to each other. Okay, the next one over cannot pull up tightly to the first one. So the shape forces them to be farther away, and the dispersion forces are going to be much less. Okay, so if you compare these two, this one has much larger dispersion due to its shape, which means it has stronger intermolecular forces. All right, so shape affects it. All right, and finally, why don't you do some practice here with these problems. The first one is identify the name of the intermolecular force, and the second part is comparing molecules and saying which one has a greater intermolecular force. So stop the video along the way and practice these. What is the force here? All right, CH3OH. It would be useful to draw a structure and see that we have here an oxygen bonded to a hydrogen, so that can have hydrogen bonding. CF4. We notice that that is a nonpolar molecule, therefore its only intermolecular force would be dispersion. And I should say that I'm asking for the greatest intermolecular force because they all do have dispersion. All right, how about CH3F? Since you do not have the same group around there, that is a polar molecule, and therefore it has a dipole, and it's dipole-dipole. It does have a fluorine, but it's not bonded to a hydrogen, so it's not hydrogen bonding. The fluorine has to be bonded to the hydrogen so it can pull the density away from it. Now, greater intermolecular forces. We have to look at whether or not there's a dipole, and that would involve looking at shape. Okay, it turns out PCl3 has a dipole, so it's polar, therefore it has dipole-dipole intermolecular forces. PCl5 is nonpolar, and you can tell this not by just looking, but by drawing out the structures, which we've done in another video. Therefore, if it's nonpolar, it only has dispersion. So the greater intermolecular force would be the dipole-dipole. Because remember, our first list was strongest to weakest. All right, let's look at these two. The HCl is going to be dipole-dipole. HCl has a dipole, but not hydrogen bonding. But HF does have hydrogen bonding. So that's a greater intermolecular force. And nitrogen or hydrogen, those are both nonpolar. They're both dispersion. Okay, so how else do we compare them? If they're the same type, we look at size. Nitrogen is bigger. Therefore, it would have greater dispersion forces, even though they have the same type of force.